Okay, welcome to lecture 14 on orthogonal diagonalization. Okay, so before we get into that, let's mention some properties of orthogonal matrices and matrices with orthonormal columns. Okay, so let's look at this theorem. So suppose U is an m by n matrix with orthonormal columns. Okay, so for this theorem, we're allowing the possibility that U might be rectangular. Okay? It just needs orthonormal columns. Okay. The first property is that if I have an x in Rn, okay, and I left multiply it by U, so I compute U times x, then the norm of U times x, or its length, is equal to the length of the original x. Okay. In other words, U preserves the length of x. For the second property, if I have two vectors, x and y in Rn, and I compute their dot product, and then I multiply both of them by U, the resulting dot product is the same as the original dot product between x and y. Okay, so in other words, U preserves the dot product between two vectors. Okay, and we'll get into the implications of this in a moment. So if you want to see the proof of this theorem here, I did it in a live lecture, the one on July 13th. Okay. So let's talk about an orthogonal matrices now. So an orthogonal matrix is a square matrix with orthonormal columns. Okay, so in particular, all of these two properties apply to orthogonal matrices since they have orthonormal columns. So we give a special name for matrices that are square with orthonormal columns. Really, this should be called an orthonormal matrix, but it's just standard that such a matrix is called an orthogonal matrix. So an equivalent way to define an orthogonal matrix, okay, call it Q now, is that it satisfies this. Okay, its transpose is its inverse. Okay. Okay, so let's assume that Q is an orthogonal matrix. Okay, and let's see what the implications of these two properties are. Okay, so assume Q is orthogonal, then that means since it's n by n, it maps Rn to Rn. Okay, so by the above theorem, we have that Q times x, the length of Q times x, is equal to the length of the original x. So multiplying by x, so multiplying x by Q, right, preserves the lengths of x. Okay, so let's suppose this is x here. Now, if I multiply it by Q, it's going to go somewhere on this circle, where this circle is all the vectors that have the same length as x. So let's say x has a length 1, then this is the unit circle. So if Q is orthogonal, it must map it to somewhere on this circle. Right? It just rotates it. It doesn't scale it at all. Okay. So what does the second part of that theorem apply or imply? Okay. So if Q is orthogonal, then we have this holding for all x and y in Rn. Okay. So the dot products between x and y, it determines the angle between x and y. Okay, so there's a formula that relates the cosine of the angle between these two to the dot product. Okay, so what this formula means is that multiplying by q preserves the angle between x and y. Okay, here's what I mean by that. So if I have x and y here, these two vectors, and the angle between them is theta. Okay, let's say I multiply both of them by q. Okay, then it rotates both of them, keeps both of their lengths the same, and it also keeps the angle between them the same. Okay, so these two properties are pretty special for orthogonal matrices. If you just take a random matrix and see how it affects vectors, it's almost certainly not going to preserve the length, and it's usually not going to preserve the angles between vectors. But orthogonal matrices will always preserve the length and angle between vectors. Okay, so you can describe orthogonal matrices as rotation matrices. Okay, they don't change the lengths of vectors. Okay, so here's another theorem that gives some nice properties of orthogonal matrices. Okay, so let Q be an n by n orthogonal matrix. Then we have that the determinant of Q is 1 or negative 1. Okay, and we also have that all the eigenvalues, lambda of Q, have absolute value of 1 or length equal to 1. Okay, so let's first prove part 1, which is pretty straightforward. Okay, so if Q is an orthogonal matrix, then we know this holds, right? And then I can take the determinant of both sides of this equation, right? So I do that. So on the right-hand side, I get the determinant of the identity, which is just equal to 1. On the left-hand side, by the multiplicative property of the determinant, I get that it's equal to the determinant of Q transpose times the determinant of Q. Okay. Then I remember a property of determinants that says that the determinant of the transpose of a matrix is equal to the determinant of the original matrix. So that means that this number and this number are the same number. Okay. So I can just write it as determinant Q squared. Okay. So I know that determinant Q squared is equal to 1. So determinant of Q, only two possibilities. It can either be 1 or negative 1. Okay, so that's a pretty straightforward proof of this fact here. Okay, so the second fact is that the eigenvalues have length or absolute value of 1. Okay, so most of the time, the eigenvalues of an orthogonal matrix will be complex. Okay, so by the bars here, I mean the length of the complex number. Okay, so we'll get into what that means in a second. Okay, so here's the proof. Okay, so suppose that we have this equation. So that means that x is an eigenvector of Q with eigenvalue lambda. Okay, so let's write down the length of Q times x. Okay, so if I write down the length of Q times x, well, it's equal to the length of lambda times x, right? I'm just subbing in qx equals lambda x into here, because it's an eigenvector, right? Now, I just use a property of the length that we discussed in one of the first lectures, is that if you have a scalar number here, lambda, I can pull it out, but I have to take the absolute value, lambda. Okay, so here's an expression for the lengths of q times x here. Okay, well, here's another expression for the length of q times x. It's just x, right? Remember the first theorem we talked about? Orthogonal matrices preserve the length. Okay, so we know that this is just directly equal to this. Okay, so we have two different expressions for the length of qx. That means this and this have to be equal. Okay, so I set them to be equal, right? And then this implies that the absolute value of lambda is equal to 1, right? Because we can just, okay, so since x is a non-zero vector because it's an eigenvector, right? I can just divide both sides by the length of x, right? So divide both sides by the length of x. So it cancels out over here, and it becomes 1 on the right-hand side, and that shows that the absolute value of lambda equals 1. Okay. So I mentioned that for orthogonal matrices, you're usually going to get complex eigenvalues. So in this case, we interpret the absolute value to be the length of the complex number in the complex plane. Okay, so if lambda happens to be complex, so it will be of the form a plus bi, right? Then the length of lambda, the complex number, is going to be this expression here. Okay, and that will always equal 1. So it should make sense that rotation matrices, such as this example that we've seen in the assignment, usually don't have real eigenvalues, right? Because suppose you rotate every vector by 45 degrees, then there isn't any vector staying in its span, right? Since it's just being rotated, not being scaled. Okay? So it makes sense then that to describe the eigenvalues, we're going to have to use complex numbers. Okay, so here's the example from the assignment. Okay, and it rotates by theta many radians. Okay, and as you showed on the assignment, the determinant of this guy is equal to 1. Okay, and its eigenvalues were complex, and you may have worked out that they have this form. And every complex number of this form will have length 1, just by the Pythagorean trigonometric identity. Okay, so this is an example of a rotation matrix in R2, and it is orthogonal, right? So we said that the determinant is either equal to 1 or negative 1. Okay? So how do we get a negative 1 determinant? What does that mean? Okay, so there are two types of rotations. Okay, so there's the rotation where you rotate the entire space by some angle, and there's also known as reflections or improper rotations, where you flip the whole space or reflect the whole space about some line. Okay, so if you're just doing a normal rotation by some angle, you'll have determinant 1. But if you're doing a reflection or an improper rotation, so this is an example of that, a reflection about the line x equals y, you'll have a negative determinant, negative 1 determinant. So those are the two sort of varieties of rotation matrices. Okay, so let's move on to the main topic, which is orthogonal diagonalization. Okay, so let's recall what regular diagonalization is. Okay, so if a square matrix has n many independent eigenvectors, okay, so a full set of independent eigenvectors, then it's diagonalizable. In other words, we can write it, factorize it like this. A equals PDP inverse, where P is an invertible matrix made of the eigenvectors, and D is a diagonal matrix with the eigenvalues along the diagonal. Okay, so now we want to ask, when is it possible that this P could be an orthogonal matrix instead of just being an invertible matrix? Okay, so in almost all the examples we've done so far, the eigenvectors were not orthogonal. Okay, so if they are orthogonal, okay, then that means we can normalize those eigenvectors, okay, and so this P becomes an orthogonal matrix, Q. Okay, so for some rare matrices, this does happen, and it is possible. But for a matrix you pick at random, it won't happen. So in this special case, we get orthogonal diagonalization of A. That means we can write A equals Q D Q inverse, where Q is orthogonal and D is diagonal. But since Q is orthogonal, that just means that its inverse is its transpose. And so we can write A Q D Q transpose. And being able to do this actually saves a lot on computation. Because if we want to factor it like this, then usually this P is not orthogonal, and so we have to compute the inverse of a matrix to be able to factorize A like this when it's diagonalizable. Okay, but if it's orthogonally diagonalizable, then the inverse just comes for free, right? It's just the transpose of Q. Okay, so this is another instance where orthogonality saves a lot on computation. So the next obvious question to ask then is, what are the matrices that allow for orthogonal diagonalization? Okay, and it's actually pretty straightforward to answer this. Okay, so this is all we have to do. Okay? Suppose that A is orthogonally diagonalizable. Okay, so that means we have this expression for Q orthogonal. Now let's try taking the transpose of both sides of this expression. Okay, we take the transpose of A, and we take the transpose of the right-hand side like this. Then we use the properties of transpose, right? We have to flip the order, and then apply the transpose to each factor like this. And so we get Q transpose transpose, the transposes cancel, and so we get this, Q D Q transpose. This is exactly what we started with though, right? So that means that A transpose is equal to A. Okay, so that gives us our answer, right? If we assume that A is orthogonally diagonalizable, we must have that A is equal to its transpose. In other words, A must be symmetric. Okay, so this proof here shows that if A is orthogonally diagonalizable, that implies it must be symmetric. It doesn't say that every symmetric matrix is orthogonally diagonalizable, though. Okay, but it turns out that is true. Okay, this condition and this condition are the exact same thing. Okay, so here's a theorem that says that a square matrix A is orthogonally diagonalizable if and only if A is symmetric. Okay, so what we wrote up here proves the forward direction, and proving the other direction is a bit more work. Okay, and so in assignment 3, you'll be helping prove part of the other direction, proving that every symmetric matrix is diagonalizable. Okay, so another important fact about symmetric matrices, okay, and a fact that's needed for this direction as well, okay, is that if A is symmetric, then if we have two eigenvectors from different eigenspaces, those two eigenvectors have to be orthogonal. Okay, so it's a piece of proving this direction, but we need this piece. Okay, so here's how we prove this. Okay, so suppose we have that AV1 equals lambda 1 V1. In other words, V1 is an eigenvector with eigenvector lambda 1. And suppose we have another pair, V2 and lambda 2. And we assume that the lambdas are different. So lambda 1 does not equal lambda 2. What we want to show is that since A is symmetric, the V1 and the V2 are actually orthogonal. Okay, that's not true for most matrices, but it is true for symmetric matrices. Okay, so here's how we prove this. Okay, so let's start with the expression lambda 1 times the dot product of V1 and V2. Okay. Now I can rewrite it like this. Okay, so what have I done here? Well, remember this rule here, right? If we have A dot B, okay, a dot product, that's equal to A transpose times B, a matrix product. Okay, so you should feel comfortable going back and forth between these because it's needed for a lot of proofs and problems involving orthogonality. Okay, so here we have this vector, that's the A, dot this vector, that's the B. Okay, so applying this rule, I take the transpose of the first part and I multiply it by the second vector. Okay, now I have lambda 1 times V1 by the Eigenvector equation. This is equal to A times V1, so I put that in here. Okay, now I spread the transpose to the factors like this. Okay, and remember I have to reverse the order. Now I have a A transpose. Since I'm assuming A is symmetric, I can replace A transpose with just A. Now I have A times V2, which is equal to lambda 2 times V2 just by this equation up here. Okay. Now I'm going to move lambda to the left. Okay. Since lambda is a scalar, it's okay to move it around the matrix equation like that. Okay. And then I'm going to use this rule again, but in reverse. right? I have a V transpose times V2. So I'm going to turn that into V1 dot V2. Okay, so what does all this show? It's shown that lambda 1 times V1 dot V2 is equal to lambda 2 times V1 dot V2. Okay, so what does that show? Okay, so this is what we just showed. Now, if I rearrange this, just subtract this part from both sides, and I get this expression. And then I factor out the V1 dot V2 that's common to both of them, and I get this expression. Okay, and now I have lambda 1 minus lambda 2. Okay, since we assumed that lambda 1 and lambda 2 were different, that means that lambda 1 minus lambda 2 is non-zero. Okay, so we have a non-zero number times this number, v1 dot v2, equal to 0. Therefore, we conclude that v1 dot v2 has to be 0. Okay, in other words, we conclude that v1 and v2 are orthogonal, just as we wanted to prove. Okay. Okay, so now we'll prove one more remarkable fact about symmetric matrices. And the fact is that they have real eigenvalues. Okay, so we'll never get complex eigenvalues from a symmetric matrix. Okay, so we'll walk through a proof of that. So a real n by n symmetric matrix has n real eigenvalues counting multiplicities. Okay, so throughout this course, we've always been assuming real matrices. Okay, matrices with real entries in them. Okay, but we're just emphasizing it here because we're comparing it to its real eigenvalues. So this part is something we've always been assuming, but now we're just emphasizing it here. Okay, so here's how we're going to prove it. Okay, so if we let A be a n by n symmetric matrix, and then we write the eigenvector equation, ax equals lambda x, and we ask, could lambda be a complex number? Okay, so let's just assume it is a complex number. Okay, let's just assume lambda has the form a plus bi. That's an eigenvalue of a. Okay, so I'm going to introduce some notation here. So lambda bar is going to be the complex conjugate of lambda. This just means we flip the sign of the bi part so that it's the opposite sign. That's what the complex conjugate is. Okay, so if lambda is complex, then that means x, its corresponding eigenvector, will also be complex as well. Okay, so x bar is the conjugate of x. It means the conjugate of each entry in x. Okay, so here's how we're going to prove that the eigenvalues are actually purely real. Okay, so we're going to start with the eigenvector equation. Okay, and if we just look at it, here's what we can do. We can left multiply by x conjugate transpose and get this equation here. Okay, so that will be our first equation. Okay, what else can we do with it? Okay, we can take the conjugate of both sides of this expression here to get this. Okay, so we get a times x bar equals lambda bar x bar. So I don't write the conjugate of a because since I know A is a real matrix, the conjugate is just equal to A, right? So I don't need to write A bar. The rest are potentially complex, so that's why I write A bar. Now I take the transpose of both sides of this matrix, or this equation. Okay, so take the transpose of this, get this. Take the transpose of this, you get this. Okay, so I don't write the transpose of lambda bar because the transpose of a scalar is just itself. Okay. Now, since A is symmetric, I substitute in A for A transpose here. Okay. Now I notice that I have this equation here, and it's very similar to this equation here. Okay. If I wanted to make them as close as possible, what I need to do is right multiply by x. Okay. So I do that, and I get this equation, and so I have these two equations. Notice the left-hand side of both equations are exactly the same, but the right-hand sides differ just by the bar over the lambda. Okay, so that implies that this and this are the same. Okay, so this and this are the same. And now I'm just going to rearrange both sides slightly. I'm just going to put the scalars in the front. Again, I can move scalars around an equation. That's fine. Okay, and this implies that lambda equals lambda bar. Okay, so why can I do that? Well, this part here is just a dot product, a number, and I know this number is not going to be 0 because I'm assuming x is not 0 because it's an eigenvector. Okay, so lambda equals lambda bar. That means a plus bi equals a minus bi. Okay, and the only way this can be true is if b is equal to 0, right? So that means lambda is just equal to a. In other words, lambda is a purely real number. It has no complex component to it. Okay, so I know a lot of the steps here are kind of unmotivated, but what you should get from this is that you should be convinced that this theorem is true. A symmetric matrix only has real eigenvalues. Okay, and now I'll present what's called the spectral theorem for symmetric matrices. Okay, so the spectrum of a matrix is the set of its eigenvalues. So the spectral theorem for symmetric matrices is a classification of all its eigenvalues. Okay, so this theorem just collects all the theorems we proved above. Okay, so A has real eigenvalues, and A is orthogonally diagonalizable. Okay, so if A is a symmetric matrix, we can write it as a really nice factorization. Okay, a product of Q, D, and Q transpose, where Q is orthogonal. Okay, there's another nice way to decompose a symmetric matrix A. Okay, and it's a way of writing it as the sum of certain matrices. Okay, so this, what we'll show now, is called the spectral decomposition of a symmetric matrix. Okay, so if A is symmetric, then we know it has an orthogonal diagonalization. Okay, it looks like this. Right? So we can write Q like this. Right? Its columns are orthonormal eigenvectors of A. Then we have its eigenvalues on the diagonal here. And then Q transpose is just its orthonormal eigenvectors, but now they're rows instead of columns. So just multiply this out and see if we get something. So if I multiply the first two matrices, right, I just scale each column by its corresponding eigenvalue, like this. Okay, and now how do you multiply these two matrices? Okay, so we talked about two different methods for multiplying matrices, right? There's the dot product method, right? And then there's the column method. Okay, so there's two different methods we discussed. There's actually a third method that we didn't mention, but we should mention here. Okay, so this is the column row expansion of the product. Okay, and it works like this. Okay, if you have the left matrix written as columns like this, and you have the right matrix written as rows, as we do, then you can write it as a sum. Okay, and the sum is column 1 of row A times row 1 of B, and then column 2 of A times row 2 of B, and so on. And you just take the sum of these products. Okay, so that's what we're going to do here. Okay, and so it becomes lambda 1 u1, so this column, times the first row, u1 transpose. Okay, we just sum that up from 1 to n, and we get this summation. So this sum has a special name, and it's called the spectral decomposition of A. Okay, and the sum, or the terms here, have a special form we should recognize. Okay, so we're taking lambda 1, okay, so a scalar, times u1 times u1 transpose. So this part right here should be familiar, right? This is what we called the outer product before, okay? And it was what we needed to compute the projection onto a vector, okay? So remember, when we were projecting onto the vector A, what we did to compute the matrix that did that was take A times A transpose, and that gave us the matrix that projects onto the span of A. And that's what we're doing here. We're computing the matrix that projects onto the span of U1. Right? So this is a projection matrix, an n by n projection matrix, right? That will be of rank 1. Okay? And that's what each of these are. Projection matrices onto the eigenvectors. Okay? So we can describe what this is saying is a symmetric matrix is a sum of projection matrices onto its eigenvectors. Okay, so this is very special, right? It's saying that A can be completely described in terms of just its eigenvalues and eigenvectors. Okay, and if we had an x in Rn, and we wanted to compute A times x, okay, one of the ways to think about it is we're taking that x, projecting it onto u1, the first eigenvector, adding it to the projection of x onto u2, adding it on to the rest, right? Okay, so I'll emphasize that if A is a symmetric matrix, then it's completely understood in terms of its eigenvalues and eigenvectors, right? If we have this factorization, right, then it's a product that's completely composed of eigenvectors and eigenvalues of of A. And if we choose to decompose it like this, we get, a sum of projections onto the eigenvectors that are scaled by the eigenvalues. So symmetric matrices have a lot of structure to them that's completely understood in terms of eigenvalues and eigenvectors. Okay, so let's work through an example, or show an example. Okay, so let's let A be this matrix here. Okay, so right away we can tell it's a symmetric matrix. So what does that mean? We know for sure it's orthogonally diagonalizable. We know for sure it has real eigenvalues. Okay, so let's diagonalize it and write its spectral decomposition. Okay, so you can check or verify for yourself that the two eigenvalues are 6 and -4. And if you do the normal method of computing eigenvectors, you'll get these two eigenvectors. Okay? But if we want to orthogonally diagonalize it, we have to normalize those eigenvectors, right? So we can get an orthogonal matrix Q. So it's not too hard here. We just divide by the norm. Okay. And then we get Q composed of these normalized eigenvectors as the columns like this. And then we get the diagonal matrix eigenvalues. And then our Q inverse is going to just be Q transpose. Okay. In this case, Q happens to be a symmetric matrix, but that's just a coincidence. That usually won't happen. Okay. Okay, so this is the orthogonal diagonalization of A. If you multiply this out, you'll get that you'll get this back. Okay, so let's look at the spectral decomposition. Okay, so this is the formula for it, since we have two eigenvectors. Okay, so remember, when we compute the outer product like this, right, it's going to be an n by 1 column times a 1 by n row. Okay, and the result will be an n by n matrix. Okay, so this matrix right here is the projection matrix onto U1. Okay, that's what we're computing here on this part. And so we also compute the projection matrix for U2 over here. Okay, and then we just fill in what the equation wants. Okay, put in the two eigenvalues here. Then we get these two matrices here, and we sum them. Yeah, we get back A.